Hello everyone, and welcome back to the Deep Learning for Teens video series. In this video, I'll explain the main parts of convolutional neural networks, also known as CNNs. In the last video, I described what a convolution is. As you may recall, it involves an activation function. Over here, we see a convolution done, and then the ReLU activation function applied to it. In the rest of the video, I will not show the activation function for convolutions to keep things simple. Just realize that when I show this, I am implicitly including the activation function. For one image, we can actually do convolutions with multiple filters, as you can see here. So with 3 filters, I get 3 outputs. To make things easier, let's ignore the numbers inside the pictures and filters. We can now do another layer of convolutions. Notice that each layer of convolutions creates a smaller output image. The input image was 8 by 8 pixels, and the first convolution output image was 6 by 6 pixels. Likewise, the second convolution output image was also smaller than the previous, in this case 4 by 4 pixels. To understand why the second convolution output is 4 by 4 pixels, let's take a look at how many times the filter can go across the second convolution's output. Over here, you can see that the filter is placed in the top left corner. This creates the first output pixel in the convolution output, shown by the red square. Here, we slide it to the right by 1 pixel, creating the red pixel shown in the output. We slide the filter a third time, and eventually our filter reaches the end of the input image, giving us 4 output pixels in one row. This is why the second convolution output is 4 by 4 in size. Just as we used 3 convolution filters in the first layer, we can use 3 convolution filters in the second layer. These are labeled filters 4, 5, and 6 in this picture. To keep things simple, we can show the filters and output stacked. We should apply the second layer filters to all convolution outputs of the first layer. Because the first convolution layer has 3 filters, we get 3 output images in the first convolution layer. The second convolution layer also has 3 filters, which are applied to the 3 output images from the first convolution layer. This gives us 9 output images in the second convolution layer. For more complex convolutional networks with larger input images, more layers, and more filters per layer, the number of computations needed become very high. To reduce the number of computations, we try to reduce the convolution output sizes. This is done using a process called pooling. In this picture, after pooling our first convolution layer output images, they are now 3 by 3 pixels instead of 6 by 6 pixels. These 3 by 3 outputs are shown in the red box. Because of the smaller outputs from the first layer after pooling, the second layer filters are also smaller, and the outputs are also smaller. Notice that the second layer outputs are now 2 by 2 images, as shown in the red box. Without pooling, the second layer output images were 4 by 4 images. This shows how pooling reduces the number of computations in the network. Now, I will explain the pooling process in more detail. Over here, you can see that we are doing a convolution on a 7 by 7 image with a 3 by 3 filter. The output is 5 by 5 in size. After pooling, we will have a smaller output. In this example, we will do pooling using the 2 by 2 red square. We first find the maximum value inside the red square. In this example, this is 3.45. We take just that maximum and put it in the pooled output. We then slide the red square so it is looking at completely new pixels. We find the maximum, which is 2.69, and put it into the pooled output. In this case, we are sliding the red square to the right by 2 pixels. This means we have a stride of 2. Once again, we slide the red square and put the maximum value inside the pooled output. We can ignore the parts of the red square that are outside the image. Now, we can move the red square back to the beginning and down 2 pixels, since we have a stride of 2. After finishing the pooling process, we have a smaller output image as shown. Let us now build up a full convolutional neural network. We start with the input image and go through the first convolution layer. This layer has 3 filters, generating 3 convolution outputs. We then apply pooling to reduce the sizes of the convolution outputs. We then go to the second convolution layer, which also has 3 filters. Notice the same three filters, 4 to 6, are applied to each of the three pooling outputs from the first convolution layer. The second convolution layer produces 9 outputs in total. If you look at the images inside the red box, you will see that there are 12 pixels in total. We can take all 12 of these pixels and line them up as shown. Doing this is known as flattening. We flatten all 9 images from the second convolution layer, and this gives us 36 pixels in one line, and this is known as a flattened layer. After the flattened layer, we usually have one or more dense layers. To do this, we first add some dense layer neurons. In this picture, we have 4 dense layer neurons shown. Each dense layer neuron is connected to all the pixels in the flattened layer. The outputs from the 4 dense layer neurons are the final outputs of our CNN. Therefore, what you are seeing in this picture is a full convolutional neural network. It has most of the key parts of a CNN, including convolution layers, pooling layers, flattened layers, and dense layers. In the next video, I'll explain how to build and train a CNN using TensorFlow. We will look at how to extend the previous ANN for MNIST into a CNN.